All right, so for chapter 9.4, the two simplest particles in chemistry are the proton and the electron. We learned these way back in chapter 2. So, acid and base chemistry involves the transfer of protons, which we have learned are the same as hydrogen ions, between acids and bases. But many other reactions involve the transfer of electrons instead. These electron transfer reactions are known as oxidation reduction reactions, or redox reactions as I call them and many people call them. Most of the combination, decomposition, and single displacement reactions that we talked about earlier in this unit, so our single displacement reactions where we had one element, essentially, one solid element, usually metal, reacting with a ionic compound, and the ionic compound splitting apart to form a different element and a new ionic compound by transferring usually a anion. We saw some of those in our single displacement reactions that we first discussed in chapter 9.1 last time. All right, so those are redox reactions. We didn't talk about redox reactions yet, but now we'll explain why those are redox reactions. So oxidation is the loss of one or more electrons from a chemical species, and reduction is the gain of one or more electrons. So let's consider the single displacement reaction that involves zinc metal and a solution of copper nitrate. If we put a piece of zinc metal in a solution of copper nitrate, you're going to end up getting a coating of copper metal on the surface of the zinc metal. And that looks like this. So this image here, copper nitrate is this pretty teal blue color, and the zinc metal is that strip of metallic zinc that you see in the test. The blue colors start to fade, and this, I don't know, spiky formation of metal on top of the metal strip. And when we let the reaction continue, you see that the solution becomes colorless, and we have more solid forming on that metal strip. So that is, we are getting rid of our copper ions in solution and forming zinc nitrate instead. And the metal that is being deposited on the surface is copper metal. So our zinc metal is reacting with copper nitrate to form copper metal and zinc nitrate. Our complete reaction is this one up here. We have zinc solid and copper nitrate, aqueous, reacting to form zinc nitrate, aqueous, and copper solid. In our net ionic equation, I'll explain this in a few slides, but we've seen before how spectator ions work. Our nitrate ion is a spectator ion, so we can get rid of it and have our net ionic equation just being those metals reacting. So in this redox reaction, zinc is giving up 2 of its electrons to form zinc 2+. So when we have a ion, that means we've lost electrons. We don't gain protons, we just lose electrons. And we have the zinc 2+ ion forming. The copper 2+ ions are gaining those 2 electrons from the zinc. When we gain electrons, it decreases because electrons are negatively charged. So we're going from copper 2+, which has no charge. It's a 0 charge. Thus, the zinc was oxidized and the copper 2+ ion was reduced. So oxidize is when we lose electrons and reduce is when we gain electrons. One little trick to remember that I learned in school was that Leo, the lion, so loss of electrons, is oxidation. So Leo the lion goes grr. So gain of electrons is reduction. So remember, L with O, G with R. Leo and grr. Leo the lion goes grr. So loss of electrons is an oxidation. Gain of electrons is a reduction. All right, so that's what we see here. Zinc is losing 2 electrons to become positively charged. Copper ion is gaining 2 electrons to become neutral, so to decrease in. All right. So in order for one species to be oxidized and give up its electrons, the other species gain those electron acceptor species. The thing that is taking the electrons is called an oxidizing agent. And that means that it is oxidizing the other species. So the other by this electron acceptor. And because the oxidizing agent is gaining electrons, it is reduced. So oxidizing agents are reduced, and reducing agents are oxidized. The reduced donates the electrons instead of taking the electron. So it gives away its electrons, which means that it is oxidized. It lost its electrons. So your oxidizing agent is reduced in the reaction, and your reducing agent is oxidized in the reaction. So that's summarized here. An oxidizing agent oxidizes the other substance, which means that it is reduced. Because one is oxidized, the other is reduced. A reducing agent reduces the other substance, so it is oxidized. They're opposites, always. All right, so in our reaction that we just saw before with zinc and copper, so zinc solid is losing its electrons, it's being oxidized. Copper is gaining its electrons, it's being reduced. Gain, reduce, lose, oxidize. Leo the lion goes grr. All right, so the thing that is being oxidized is reduced. The thing that's being reduced is the oxidizing agent. It's oxidizing the other species. All right, so the equation for a redox reaction can be broken into half reactions. A half reaction shows only the species involved in the oxidation or the species involved in the reduction. So you have a half reaction for oxidation and a half reaction for reduction. And in these half reactions, this is where we see the electrons. So we don't see the electrons in the net ionic equation or even the balanced equation because they are not a chemical species. But in these half reactions, we can see the exchange of electrons. When you add the two half reactions together, that is how you get the net ionic equation. So in our half reactions for zinc and copper, so the oxidation half reaction, the thing that is being oxidized. So Leo, the lion goes grr. Zinc is losing its electrons. The electrons are a product. And zinc is being oxidized. So that makes this the oxidation half reaction. All right. And copper is being reduced because copper is gaining electrons. The electrons are being added, so they are a reactant. So gain of electrons, this is the reduction half reaction. So for the oxidation, the electrons are a product. For the reduction, the electrons are a reactant. But when we add them together, they're just like our spectrons. They're the same on both sides of the equation, so they don't show up in our net ionic equation. Okay, so why do we call this oxidation? The term oxidation originally referred to the addition of oxygen, so it's probably what you thought when you first heard oxidation. Sounds like oxygen. Oxygen is a very common oxidizing agent. It's the most common, especially in nature, the most common you'll ever encounter. It's how we make iron oxide, which is rust. So iron solid, oxygen gas gives us iron oxide, which is Fe2O3, because it's usually the 2 plus version of iron, but you guys don't need to know that right now. So that is one example of oxidizing that happens very often in nature, as you've seen, I'm sure, with lots of rusty metal, rusted car parts, rusty benches, etc., etc. All right, so when oxygen gas reacts with a metal, each oxygen molecule gains 4 electrons. So 2 electrons are gained for each oxygen atom, and that causes us to gain O2 minus ions, our oxide ions. So 2 electrons for each oxygen atom reduces the charge on oxygen to 2 minus. Our halogens, fluorine, chlorine, bromine, and iodine, so fluorine and chlorine gas, and then bromide is actually a liquid and iodine is actually a solid, but all of those are also good oxidizing agents. Metals are usually good reducing agents. So metals are usually being oxidized by oxygen or reducing the oxygen to oxide ions. All right, so they are good reducing agents because they're oxidized to form positive ions. We have already seen that metals like to be cations based on our electron configuration, if you remember back to chapter 5. All right, so alkali and alkaline earth metals are group 1A and group 2A elements are excellent reducing agents. So is aluminum. On the other hand, your coinage metals, so copper like in a penny, silver, and gold, are poor reducing agents. That's why they're useful for making coins. They don't oxidize easily or corrode. They're very stable, so that's why we use them in coins. In cases involving complex compounds and ions, the electron transfer can be difficult to discern. So one way to help you figure out what the oxidizing and reducing agents are is to look at something we call oxidation numbers. It's a system of electron counting that we use to identify which species gain or lose electrons in a reaction. So oxidation numbers, also called oxidation states, represent the number of electrons that have been gained if the oxidation number is negative. So a negative oxidation number means it gained negatively charged electrons, or lost if the oxidation number is positive. So if it lost electrons, its charge went up because it lost some negative charge. All right, so oxidation numbers are primarily used to identify the transfer of electrons in a redox reaction. So don't think about oxidation numbers as a charge on an atom in the compound. They are just for determining whether electrons were transferred. They do not always represent the charge on the atom. Sometimes they do, but not always. So here are our rules for assigning oxidation numbers. Each atom that is a pure element has an oxidation number of 0. So iron in solid iron is an oxidation number of 0. Oxygen in oxygen gas has an oxidation number of 0. All right, what's our next rule? A monoatomic ion has an oxidation number equal to the charge. So a monoatomic ion, an ion that consists of one atom. It's not our polyatomic ions that are covalently bound. It's one atom that makes an ion, like chlorine in chloride and magnesium in magnesium ion. So chlorine, based on its position on the periodic table, it's a halogen. It is a group 7A, so it a -1 oxidation, which is what we usually see as its charge. And magnesium is group 2A, so it's a +2, which is the same as its charge. All right, so like we said for chlorine, in compounds, halogens usually have an oxidation number of -1. So if the halogens are with carbon or hydrogen or a metal, then typically that halogen is going to have a -1 charge. The only exception is when halogens are combined with oxygen or fluorine. So here's an example. Each chlorine molecule, or the chlorine molecule, in chlorine trifluoride has a +3 charge. So you can tell that because the fluorines are what are typical halogens. They have a -1 oxidation state, and it's a neutral atom, it's a neutral compound, so the oxidation states have to add up to 0. And we'll see that again in rule number 6. All right, so in compounds, oxygen usually has an oxidation number of -2. So it usually has the same charge that, or same oxidation state as its typical oxide charge. However, there's one exception in compounds containing the peroxide ion. So you've probably heard of hydrogen peroxide. There are other peroxides, but the most common one is hydrogen peroxide. It has this O2 ion. And that O2 ion means that each oxygen has a -1 charge. So we get a +1 from the hydrogens, which we'll see in the next rule, and a -1 from each oxygen in hydroxide. So you won't have to think too often about these exceptions. So I would focus on the main rule, but you might need to, so I'll highlight the main part of the rule with these arrows, but the exceptions are good to know. All right, so when combined with nonmetals, hydrogen is assigned an oxidation number of +1. So when we see hydrogen in methane, for example, hydrogen is a +1. When we see hydrogen in water, or even hydrogen in our peroxide, hydrogen has a +1 because carbon and oxygen are nonmetals. But when it's combined with a metal, hydrogen has an oxidation number of -1. So when it's combined with lithium, it has an oxidation number of -1. That is called the hydride ion. So that is when hydrogen takes on its characteristics of halogens, because technically hydrogen is on both the far left side of the periodic table and the right side, because there's only 2 elements at the very top of the periodic table. Anyway, our final rule is that the sum of the oxidation numbers for all atoms in an ion is equal to the charge of the ion. So that's this one right here. So the perchlorate ion down here is a -1 ion. So our charge has to, or our oxidation numbers have to add up to -1. And we saw earlier that oxygen has a -2 charge and a -2 oxidation state in most compounds. So here it is also -2, and there's 4 of them. So when we multiply that together, we get -8, and the oxidation number of chlorine in the perchlorate ion has to add up with -8 to equal -1. So that means that the chlorine oxidation number or oxidation state in the perchlorate ion is +7. It's huge. But that happens. All right, so, and finally, for a neutral compound, same idea. For a neutral compound, the sum is equal to 0 because it's not an ion, it doesn't have a charge. So that's like our carbon dioxide here. So carbon dioxide, the carbon oxidation number has to add up to 0 when it's combined with the 2 oxygen oxidation numbers. So the oxygen, again, is a -2 typically. So -2 times 2 of them for carbon dioxide gives us a -4. So our carbon oxidation number plus -4 equals 0. So our carbon oxidation number is +4. And you'll see very often that that is the case because carbon is in group 4A, but don't always count on it. It's better to calculate it from the sum of the oxidation numbers for a compound. All right, so let's practice. We want to determine the oxidation number for each atom in potassium carbonate. So potassium, and potassium is one of our cations that is always soluble. So I'm going to break this apart into ions. So we have the K plus ion, there's 2 of them, and we have the carbonate ion, which is a 2- ion. So for potassium, it's a +1 ion, it's a monoatomic ion, so its oxidation state is +1. Okay, now let's look at carbonate. So oxygen, this oxygen is not a peroxide, so this oxygen has a -2 oxidation state. There's 3 of them. So when we add them up with carbon oxidation number, we should get -2 because our ion has a -2 charge. All right, so let's find out what carbon's oxidation number is. So we have 3 oxygens at -2 each, so that's -6 equals -2 number. The carbon in a box here. So if we add our 6 to the other side, we see that, like we expected, carbon is a +4. So our oxidation numbers are -2, +4, and +1. So potassium is +1, carbon is +4, and oxygen is -2. So we can just double check to make sure that our compound adds up to 0. We use the ion to find out what carbon was, but our compound should add up to 0. So if we have 2 potassiums at +1 each, plus +4 for carbon, plus 3 times -2 for oxygen. So that's 2, that's +2, plus +4 is +6, plus -6 equals 0. So we're done. So potassium +1, oxygen minus 2. Carbon plus 4. Let's see what we get for barium permanganate. So that's the permanganate ion. You didn't have to memorize it, but it was one of our polyatomic ions that I said might be useful to remember. So barium is going to be, barium is typically a 2+ ion. So I'm going to assume for now that it's a +2 oxidation state. We can check it at the end. All right, and then permanganate is a -1 ion because you can see there's 2 of them to balance out 1 barium. So 2 times -1 equals our +2 on our barium. Well, equal and opposite to add up to 0. Anyway, so this is our peroxide. So oxygen, again, is -2. And we're going to see what manganese is. So I'm going to put manganese in a box this time. Manganese plus 4 times -2 is going to add up to our charge of -1. Okay, so manganese, whatever its oxidation state is, plus -8 is going to equal -1. So then if we add 8 to both sides, see that manganese oxidation state is a whopping +7. All right. So let's just double check. I'm going to erase here to see. Let's just double check that it adds up to 0. So we have 1 barium. So that's +2, we think, because it's a 2A element. Okay. And we're adding it to a +7 for manganese, but there's 2 of those. Okay. And we're adding it to 8 because we have a coefficient of, or sorry, a subscript of 4 on the permanganate ion for oxygen and a subscript of 2 for the whole ion. So there's 8 oxygens. So that's 8 times -2. And this should equal 0 if we did it right. So +2 plus 14 plus -16. So +2 and +14 equals +16. And we add it to -6 and get 0. All right. So we have +2 for barium, +7 for manganese, and -2 for oxygen. Okay. All right. So just to finish up here, we can usually predict the products of acid-base reactions or precipitation reactions like we've shown before. So acid-base reactions usually produce water, and precipitation reactions usually produce an insoluble product. So we can usually predict those products because it's a reaction. So we have an exchange of ions between the 2 compounds. Anyway, this is not the case for redox reactions. Redox reactions are much harder to predict the products for, so it's not really something we expect you to do. But if we give you a whole reaction with reactants and products included, you should be able to predict when one might occur. You should be able to predict that the reaction would be a redox reaction, and you should be able to recognize one when you see it. All right, so the way that you can either predict one from reactants or recognize one from an entire reaction is that redox reactions always involve a change in the oxidation number of one or more of the atoms. Therefore, to determine if a reaction is a redox reaction, you have to first identify all the oxidation numbers, and then you have to see if the oxidation numbers change from reactant side to product side. So you want to find the oxidation numbers of all elements on both sides of the reaction, and then see if the oxidation numbers for any one or more elements slash atoms have changed. If so, it is always going to be a redox or oxidation reaction. Oxidation reduction reaction. All right, let's take a look. For example, look at this reaction. Chlorine gas reacting with a acid, an arsenic-based acid, and we're forming arsenic acid, and what's this? Hypochlorite? Hypo, I don't actually. Um, so these oxo acids always get me. Anyway, so first we want to identify the oxidation numbers. So chlorine gas is a element. It's a natural, it's the way you would find chlorine in nature. All right, so that gives it a 0. All right, hydrogen is with nonmetals here, so it's a +1. Oxygen is not a peroxide, it's a 2. And we'll skip arsenic for now, but on the other side, again, we have hydrogen that's a +1 and oxygen that's a -2 because they're not a peroxide, and the hydrogen is with nonmetals. And finally, we've got +1 hydrogen again, and minus again because it's not a peroxide and they're all nonmetals. So how do we find the remaining ones? So it's going to be just what we did before. So H3AS, so arsenic is AsO4. The sum of the oxidation states here is going to add up to 0. So that's going to be +1 times 3, because there's 3 hydrogens, plus whatever arsenic is, its state, plus 4 times -2 for oxygen. Okay, so that's +3 -8. Arsenic is a -5. Sorry. So we have -5 plus the arsenic oxidation state equals 0. So to balance that out, we add our 5 to the other side. And we see that arsenic is a +5 in that molecule. We do the same thing for the other two to find out what this arsenic and this chlorine gave them to us here. So that arsenic becomes a +3 oxidation state, and this chlorine becomes a +1 oxidation state. Because the oxidation number of chlorine increased from 0 in chlorine gas in acid, that means that the chlorine atoms lost an electron, and that means from Leo, the line goes grr. That means that it lost an electron, so it was oxidized, which by our definition means that chlorine gas was our reducing agent. Likewise, the oxidation number of arsenic decreased from +5 to +3. Because it decreased, that means that it gained electrons. So gain of electrons means that the arsenic atom was reduced. If it is reduced, that means it is the oxidizing agent. So arsenic was reduced, is the oxidizing agent. Chlorine is oxidized, agent. All right. So here are a list of common oxidizing and reducing agents and what they usually form in a redox reaction. Like we said, oxygen is a very common oxidizing agent. That's where we get the term oxidation from. And when it reacts, it forms the O2 ion. The oxide ion. Peroxide is also a strong oxidizing agent. -1 to a -2 oxidation state in water. So we form water hydrogen peroxide. Halogens are usually good oxidizing agents. Our last example showed it as an reducing agent, so don't take this as the gospel. These oxidizing agents and reducing agents are just the common ones. They're not always the case. So our halogens are oxidizing agents typically, and when they are, the products are halide ions, are -1 charged ions. And a couple others, the dichromate ion and the permanganate ion. So we saw the permanganate ion on a slide ago. And when it is in a reaction as an oxidizing agent, it typically produces the manganese 2+ ion, and the dichromate ion typically produces the chromium 3+ ion. But you don't need to know that. It's just for your reference. So common reducing agents then are hydrogen gas or any hydrogen-containing compound, and one of the products is usually the hydrogen ion or water. Carbon is often a reducing agent as well, and a product is carbon monoxide or carbon dioxide. And the most common ones that you'll see are reducing agents, which are metals. So sodium, potassium, iron. We've seen zinc and copper in these slides as well. Aluminum, these are all good reducing agents. And when they react, they form their metal ions. Okay. So finally, reactions. So if you want to be able to identify a redox reaction, these are some other surefire ways to do it without looking at oxidation states for all of your all of your atoms in the reaction. So if you see a reaction that involves a pure element, it's usually a redox reaction. It's usually going from a 0 oxidation state to something else, positive or negative. And if you have a reaction that involves atoms with a very high or very low oxidation state, so our permanganate ion, for example, had that +7 on its manganese, and that +7 oxidation is very high. It's not very stable. So it works as a very strong oxidizing agent. So as we saw on the previous slide, reactions involving the permanganate ion almost always involve it being reduced to a lower oxidation number because +7 is just not stable at all. It's very, very high oxidation state. All right, and finally, all combustion reactions and most of our explosive reactions are redox reactions. Combustion reactions, if you remember, are all something usually reacting with oxygen gas, almost always reacting with oxygen gas. And if it's a hydrocarbon, if it's an organic compound, it also forms water and carbon dioxide, which is something we learned a long time ago. But the main part here to memorize is that, or to remember, is that it's a reaction with oxygen gas. And oxygen gas, as we saw in our table, is an oxidizing agent. It's where we get the term oxidation from. So oxygen in the air is the oxidizing agent, and whatever the organic material is that's being combusted, if you have methane gas or ethanol or a piece of coal, these organic materials are reducing agents because oxygen is the oxidizing agent. All right, so one final example before we go. We want to identify the oxidizing agent and the reducing agent in the following reactions. So we're going to do this by looking at oxidation states. All right, so potassium bromide. So potassium is one of our bromine is a halogen, and it's not with oxygen or fluorine, so it's going to be a -1. Chlorine is in chlorine gas, so it's going to be a 0. Bromine is in bromine liquid, which is the natural state of bromine, so it's going to be a 0. It's a pure element. And over here we have potassium again, which is still a +1, and chlorine, which is now a -1 because it's a halogen and it's not with oxygen or fluorine. So what do we have? We have bromine going from a -1 state to a 0 state. So to go from -1 to 0, bromine lost electrons. To go from chlorine, so chlorine is a 0 and it's going to a -1. So it's going down in charge. So chlorine gained the electrons. So from our little mnemonic here, Leo the lion goes grr. That means that bromine is being oxidized and chlorine is being reduced. And from our definition of oxidizing and reducing agents, that means that bromine is the reducing agent and chlorine is the oxidizing agent. The thing that is oxidized is doing the reducing. So bromine is doing the reducing. It's the reducing agent. Chlorine, the thing that's being reduced, is doing the oxidizing. It's the oxidizing agent. All right, there we go. So let's try it again. So copper. Copper solid, copper metal, has a 0 oxidation state. It is a pure element. Bromine liquid is also a pure element. So we have 0 and 0 on our reactant side. Pretty cool. All right, and then on the right, we have copper ion. So it's a monoatomic ion, so it has a +2 oxidation state because it's the same as the charge. We have the same thing here with bromine. So we have the bromide ion, we have 2 of them, and they have a -1 oxidation state each because it's a monoatomic ion, so it's got a -1 charge and a -1 oxidation state. So copper is losing 2 electrons. It's going from 0 to a positive number, so it lost 2 electrons. Bromine, we have 2 bromines, so each one gained 1 electron. Because we went from 0 to -1. We went down in charge, so we gained our negatively charged electron. So the one that lost the electron from Leo the lion goes grr is reduced. The one that gained the electron from Leo the lion goes grr, I'm sorry. Leo, LO, lost electrons, it was oxidized. I'm sorry. And then bromine gained electrons, Gr, it was reduced. So the thing that was oxidized is the reducing agent. The thing that was reduced is the oxidizing agent. So copper metal is our reducing agent. Bromine liquid is our oxidizing agent.